Hi guys, welcome to a new video. We have this exercise this time uh, on which a cube tilts over the edge of a table. The problem says a cube with the edge length 2a and mass m glides with constant velocity v0 on a frictionless plate. At the end of the plate, it bumps against an obstacle and tilts over the edge. We want to find the minimum velocity v0 for which the cube still falls from the plate. So we have this illustration here. We have the part A of the illustration on which the cube is sliding on the table. On this second part, the cube reaches the edge of the table, and on the third part the cube starts tilting over and getting off the table. So we want to calculate the minimum velocity for which this situation happens. So first we want to write the formula for the angular momentum for a particle that is moving on a straight line. By definition, we have that the angular momentum is equal to r cross p, where r is the distance between the projection of the particle and its position, and p is the angular momentum. So we can write this by definition like p a sine of theta, where theta is, if we have this velocity right here on this direction, right, and we have the projection on this, the distance a, so the angle theta will be this right angle, and theta will be 90 degrees. So because of that situation, we have that sine of theta is equal to 1, and we have here that this is equal to PA. But we know that P is the linear momentum, and that's equal to mass multiplying velocity times A. All right, this is by definition. We can call this equation number 1, right? Okay, this is the angular momentum initially, but immediately after the collision, so on the B part of the illustration, after the collision, we will have an angular momentum that appears as rotational motion of the cube. So you see here on the first illustration that the motion is completely linear, but on this second part of the illustration, the cube starts moving and experimenting a rotational motion. So immediately after that happens, we have a momentum, but this time is angular momentum due to the rotational motion, right? So we will write the angular momentum as a consequence of that rotational motion as theta a omega 0. Here we have that theta a is the rotational inertia of the cube, and omega 0 is the angular velocity. Right. Let's call this equation number 2. as you know, the angular momentum is a quantity that is conserved, right? So using the definition of the conservation of the angular momentum, we can make equations 1 and 2 equal. Then we will have that L is equal to theta A omega 0 equal to m v0 a. So here what we have done is we have made equations 1 and 2 equal, because we know that angular momentum is a constant, right? Is a constant. Okay. From this equation, we will have that we can clear omega 0. So if we clear omega 0, we will have omega 0 equal to m v0 a dividing theta a. And let's call this equation number 3. Okay, we have this equation number 3 right here. Next step that we are going to make is we will calculate the energies of this cube. So for the kinetic energy of the cube immediately after the collision, we will have kinetic energy as the rotational motion happens. So as the rotational motion happens right after the collision, we will have a kinetic energy defined by T0 equal 1/2 of the inertia multiplying angular velocity square, right? This is the kinetic energy. Because of the rotational motion. Right, but we have right before this equation that the angular velocity is defined by this expression, right? And we call this equation number 4. So what we can do here is we can replace equation number 3 into equation number 4. When we do that, we will have that T0 is equal to 1/2 of the inertia multiplying the angular velocity square. But the angular velocity, we found the angular velocity on equation number 3. So what we do is we write equation number 3 into number 4 like this, and we know that this is a square here. So let's do this little algebra real fast. We get here 1/2 theta 0 m squared v0 squared a squared dividing theta a squared. So we can cancel this with this, right? Equation number 4 is going to be finally like this. We get T0 equal to m squared v0 squared a squared dividing theta A. And that's the final, let's see, kinetic energy, right? That's the final, this is how the kinetic energy looks like. Well, we know that the particle is moving on the table, is sliding. But if we come back to the illustration and we see that the center of mass, let's see that the center of mass of this cube is right here, right? The center of mass. The distance between the center of mass and the table is A, and it's called H1. I will highlight it right here. And that's the first distance between the center of mass and the table. We want to find the potential energy because of the weight of the particle on this situation. So that is the first part. Now if we go to the last part of the illustration, on part C, we can see that the distance between the center of mass and the table has changed, and it's not called H1 anymore. Now it's called H2, and I will highlight it also as well. So we need to calculate. It's straightforward to see that H1 is equal to A, but we need to do a little geometry to calculate H2. So we do a little bit of geometry, and we will find that H2 has the following, way. So let's see here real fast. Let's do this real fast. So this is this is H2, right? And this is 2A, and this is 2A. Let's do something like this. For example, what I'm doing is I will do it again. This is H2, right? This is 2A. This blue line is A. This blue line is A, right? And that's a right triangle. So I will make it bigger, and it's going to be like this. This is this is the distance we want to calculate. Give me a second, I will do it again like this. It's better. It's better doing it like this. There we go. Okay, this is H2. This is A. This is A. You know, by geometry, right? By geometry, it's straightforward to know that H2 squared is equal A squared plus A squared by the Pythagoras theorem. And this is equal to 2A squared. Then H2 squared is equal to 2A squared. So we take root square on both sides. Then we get that H2 is equal to A root square of 2. Right? So we have that. We come back to the next page. Okay, we do the conservation of the energy of the situation. And let's write the difference between the energy at the final point and the initial point. So let's write the potential energy as delta V equal to V2 minus, or yes, let's call it Vc minus Va, where V and A are the final and initial points respectively, and Vc is equal to mgh2 minus mgh1. This is a formula that is well known, right? Let's write delta V like, simplifying this situation, we get h2 minus h1 and we calculated that h2 is equal to a root square of two. So we will write it here, and we get this is equal to mg a root square of 2 minus this is h2, right? And h1 would be a, remember h1 is a, then we will have delta V. We simplify this equation like this, taking out common factor A, and let's call this equation number 5. Equation number 5. For the conservation of the energy, we make equations 4 and 5 equal. 4 and 5. Equation number 5 is equal to equation number 4 by the conservation of the energy. Well, when we do that, we get the following: m a g 2 square minus 1 equal to m squared v0 squared a squared dividing theta a. Let's simplify this equation like this. This mass with this mass, a with this square a, and doing that, we get then that g square 2 minus 1 is equal to m v0 squared a dividing theta a. By definition, the moment of inertia of the cube is, by definition, theta a is equal to 8/3 of the mass a squared, right? This is the moment of inertia. For a cube that is rotating around the edge, around one edge. So this is the moment of inertia. So let's go to the illustration again and see. If you see this cube is gonna rotate around this edge. So he's rotating around this edge, and the moment of inertia depends of the x of rotation. So in this case, we will, on this video, we will calculate the moment of inertia of this object in a more formal way, but we use the definition on this video. Let's go and replace this equation on the last one, on this. When we do that, we just get a g square root of 2 is equal to m v0 squared, right? Is this equation. A dividing 2 theta a dividing theta a dividing theta a. Oh, sorry, I forgot to write down the 2 over here, and now we are good. You have 2 theta a, right? This is the same equation we had before here. I don't have to write this, so now we are good. Well, now we replace this into this, and we will have g root square of 2 equal minus 1 equal to m v0 square a dividing 2. Okay, the moment of inertia is 8/3 of mass m square. Let's cancel the terms that are equal. A square. And finally we get the same. Finally we get that g to the square of 2 minus 1 is equal to v0 dividing USB 16, 2 times 8, 16 thirds of the A of the A, right? and this is v0 squared. And finally, we take this part of the equation, we move it to this side, and we will have 16/3 of the AG root the square of 2 minus 1 equal v0. And we take root square on both sides of the equation, and finally we get v0 is equal to root square of AG 16/3 root square of 2 minus 1. And this one is the velocity that the cube has to have to tilt like it does. The minimum velocity that it has to have when it's sliding on the table to tilt over when it hits the edge of the table. So this is the minimum velocity. Hopefully you can get this exercise helpful for you, and see you in the next video. Bye.